much. Oh, Deborah's here. No, it doesn't come up. I have to press admit.
Hey.
Good evening.
Is it just you and me?
As of right now, yes. We still have 2 more minutes.
Okay. Well, it usually is me and Stuart Sugarman.
Right.
But he said he had an obligation that he was going to try to change.
Okay.
But but you do these even if you want to say forget it because it's just me, it's okay. But
no, that's
if you want
fine.
to keep going, okay.
Yeah. Why not?
Okay. Sure.
Yeah, we'll wait until 6 p.m. and if we're still the only ones, we'll just get started.
Okay.
I'm gonna pull up the PowerPoint that I made.
So are you in Jackson now?
I'm actually in Tucson, Arizona.
Oh, so you're the Tucson contingent.
I am, yes.
I have friends somewhere in Arizona. I'm not sure where. If they're in Tucson, I'll figure out how to email them and tell them about you guys.
Oh,
about
fantastic.
You.
Thank you. Here we go.
And there's some, oh no, you are himself. Okay.
Yeah, I'm acting as Sam. I'm using his account.
Okay.
All right. Here is Star Trek 2009. This was supposed to be the movie that was going to be done sometime in October, but there was a scheduling snafu and we had to postpone it. But here we are in February, finally getting to watch the movie. So
I'm stopping my, yeah.
Yeah. So I'm sure you're familiar with, this is Sci-Fi Explained, and we go through the movie and analyze the scientific accuracy of some of the movie components, and we answer and ask questions about physics and astronomy as they come. Let's get to the movie here. So I have it rented on Amazon.
Mm-hmm.
We'll start from I think about 12 minutes in, and that's when we really start to see some action. Go ahead and share this window. 1 second. Oops. New share. Here we go. All right. Make sure this is.
Oh, you've got bonus features.
Yeah. Trying to get the volume to work here. Wonder why I can't hear anything. Oh, here is Stuart.
Stuart?
Here we go.
Hi, Stuart.
Hey, Deb.
Good evening.
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 So tonight we're watching the 2009 version of Star Trek. And right now I have the screen shared to the movie. I'm just trying to see how I can get the volume to cooperate.
Okay, so we're gonna. I'm Stuart. Hi. What's your
Yes, I remember you. We did a presentation back in September or October, I think.
And you did one of those. What's your name again?
Ryan.
Ronnie?
Ryan.
Ryan. Okay, yeah. Great.
Mhm.
So we want to do it just like that. If we have questions or comments, interrupt you.
Exactly. Yeah, of course. I'm just trying to get the volume to work on here. I wonder if I have to change my settings. Okay.
And I got to leave at maybe 5 to 7 or something for.
Okay.
Pre-
No problem.
Okay, good.
Can you guys hear the movie?
No,
Interesting.
and it's
Okay.
a black screen.
Should say I'm sharing this. All right, let me stop and read it.
That's
again.
you. Okay.
Okay, share this window. And you still don't hear anything?
No,
No.
and black screen. Oh,
You
This
you
whole-
don't see anything either.
no.
Huh. That is weird.
I mean, it looks like it was trying to load and then it went to black screen.
Yeah.
No sound.
Hmm. Let me see if I can move it to a new tab. Go to my Amazon this way.
Well, do you remember, we could talk about the scene if you can remember what the point was. What
Oh,
scene
sure,
and the
yeah.
point.
What I was going to talk about was the question if there can exist lightning in space. So early on, I think about 10 minutes into the film, there's this giant cloud from which the ship is passing through. And there's like flashes of lightning. It looks like a real thunderstorm.
Oh, yeah, the lightning, because that was also when his father got in trouble.
Yeah, and so the question I had, just watching it, when I watched it for myself, was, is it possible to have lightning in outer space? And I did a little research, and it turns out that yes, of course, lightning can exist in outer space. And this is the slide I had
You know,
prepared.
yeah, that's
You
very
guys see
cool.
that
Just to make
slide?
sure we're in the same movie. What movie are we doing?
This is Star Trek 2009.
First Contact, or that's different?
No,
I don't think it has like a subtitle like that. It's just
it's the first one of the new series.
Yeah, I watched it and then, so I'm going to look at the synopsis. Why? Because that was one that got canceled. We didn't do it, right? In the film.
Yes.
Yeah.
That's
Exactly.
what it starts off with Jim Kirk being born.
Yeah. I got to refresh it. I'll
Yeah.
refresh it while you're talking. I'll get it in
Okay.
my head in a second.
yes.
Okay, so lightning in space.
Yeah, so that's the question. Can you still hear me?
Yeah.
Okay, great. All right, that works. So yeah, lightning in space. It turns out that there can be electric discharges in space, even though it's pretty close to a vacuum. And so we'll just go over what lightning is in a nutshell. What what lightning is, I mean, like the bolt you see on this slide, is pretty much a zigzag pattern of plasma. And it's, charged particles, electrons, being moved really rapidly from one point to another. And it's like a stream of charged particles that are moving. And that's all it really takes. You have a negatively charged cloud and a slightly positively charged ground, or vice versa. And charge jumps from one surface to another. And that gap is known as the potential. And we can see this in outer space if we look at nebulas. So we'll go to this slide here. This is a picture of the Swan Nebula, also known as M17. And in the Swan Nebula, you can have the same types of discharges where you can have charged particles jump from one region in the nebula to another across that potential. And the result is literally a bolt of lightning. So yes, lightning can exist in outer space.
Well, because the nebula is gases, which are
Right.
particles, right?
Yes.
And the gases in the form generally of plasma with, nucleus without electrons.
Exactly. That's what a plasma is. Yeah. Just
Yeah.
loose subatomic particles moving really rapidly for lightning. Yeah. I just want to see if I can get the movie playing on one of my tabs in here, because the reason it may not have been working was it was a different window.
Where's that? Hmm.
So let me see if I can go back to here. This is the is this the right account? Switch account. Okay, that's it. Oh, here we go. Okay, this is it. Are you able to see or hear the movie now?
We had sound for a moment and
Are you able to see
then-
anything?
No. Can hear, but can't see.
No video?
Oh, there's a little video,
Huh,
mini video.
okay. It's just a black screen.
That's black,
Okay,
but loading.
all right. It may also be my connection. Okay, let me just switch my Wi-Fi here. I think that'll help. And then we should be.
Farm phone towers prepare farming equipment on workers. Yes, sir. Jim, their shields are still up. Are they?
Now, can you see the video?
They're not.
No, well, they had a moment of a mini screen.
Okay, it may just take a second for it to like transfer over the connection.
So what sets up the potential in a nebula?
It's if you charge more and more particles. So you can try this experiment at home, actually. You can create a potential. If you've ever taken like a balloon, for instance, and rubbed it on your hair, you can stick it onto surfaces. That phenomenon is pretty much the same thing, as you're transferring electrons and you're charging something. And the same effect is also if you like rub your socks on a carpeted floor, you can actually experience a potential by touching like a metal doorknob. That those electrons will jump from your finger to the doorknob.
Right. But what
So
happens in a nebula that makes that happen?
The same exact thing. The same exact thing is happening in a nebula, but on a much larger scale. Now, if you really want to get into the details of like how exactly are electrons stripped from atoms, that is like a really complicated matter that I
Yeah.
don't even think scientists have a perfectly clear explanation of why that happens. It's
Yeah,
truly
like, why would they? Unless something electrically powerful or magnetically powerful were forcing it, right?
yeah, it's really like those unlocked mysteries of the universe still. You know, we
Hmm.
have a really good understanding of how gravity works, but why does gravity work in the first place? That's a question that nobody really has the answer to. So I think
Yeah.
it's sort of diving into, why does electrostatics behave the way they do? And I certainly wouldn't be the one to know the answer to that. Let me see. I'm going to jump back in here. Let's see if I can find that lightning video. So yeah, this is when he's born. About 11 minutes into the film. Does it still look like a black screen, or can you see some video?
Before a moment ago, we could see there now a little.
It's just
Okay.
a small corner of the screen.
Yeah.
I wonder if I go full screen here. So now this is like the title frame.
I mean, you're at 27 minutes in it.
So now this is where he runs away with the car and nearly drives off a cliff.
Yeah.
Yeah, but the
Okay.
picture's lost again, but that's about where you were.
I wonder if that's just a connectivity issue. It's running smoothly on my screen. I unfortunately don't have much control over how fast it gets sent over the Wi-Fi.
Well, I mean, we could talk about stuff even without the visuals. So,
Okay. Yeah, I'm not sure why it's not sending or why it only looks like a tiny little screen. But I think the next thing I wanted to point out was I can't move.
oh, that's beautiful. I want to print. I can't make up my mind which print to request. They're all so beautiful.
Okay.
Do not forbid the bending of space in order to.
Yeah.
Oh.
What's mentioned quite a few times in the movie is this concept of traveling at warp speed. And what somebody had mentioned in the movie was, it was that guy with the Irish accent. I'm blanking on his name.
Scottish.
Scottish accent. I'm sorry. Yes.
Because his name is Scotty.
Okay. Yes, that's right.
And transporting at warp speed was something that he didn't know that he had developed in the future.
Exactly. Right. And he was like, oh, if you're traveling faster than light, how can I, beam somebody from one ship to another? And he couldn't figure it out. And it was like, hold on. Whenever somebody says traveling faster than light, usually a red flag goes up in my head and say, hold on, I think you're overlooking something. But what he really means to say is the spacecraft is simply outpacing light in a flat space. Now, Einstein does forbid you from moving faster than light speed. However, Einstein's laws don't say you can't bend space in order to get from point A to point B faster than light would through a flat space. And that's what this illustration is kind of trying to show, is this little spacecraft here is surfing on the space-time fabric, and it's pulling the space in front of it and folding the space behind it. So it's like wrinkling this fabric in order to get from point A to point B faster than light would be able to travel on that fabric. And one of the most well-known analogies to describe warping space is to picture an ant walking along a flat piece of paper. And let's say the ant is able to travel at light speed. Let's say this ant is like a particle of light. It will take some amount of time for the ant to travel from one side of the page to the other. But what you can do to the page and to space, this is the analogy, is warp or bend it. And so now the ant can travel from one side of the page to the other instantaneously, faster than light would. So Einstein doesn't say you can't do that. You can, of course, bend space and get from point A to point B faster than light would be able to. I'm going to jump to that point in the movie here. I think it was around an hour 17 when he was trying to figure out the equation.
Yeah.
For an hour 20.
So I was thinking that transporting from warp to warp would be like throwing a ball inside a ship going at warp. The ball has the inherent speed of the ship in addition to what your arm gives it.
Yeah, and that's classic Galilean relativity, where velocities simply add. But when you get to relativistic speeds, when you're traveling at 99% the speed of light, or absurdly close to the speed of light, things start to get a little crazy, and you have a lot of factors to be considered. The Lorentz factors, the real monkey wrench that gets thrown into all the equations. And so here you'll listen to Scotty trying to explain his reasoning.
I'll tell you the truth, yes. I don't know. I do feel guilty.
What if I told you that your transport theory was correct? That it is indeed possible to beam onto a ship that's traveling at warp speed.
I think a flat collision has been discovered on a hyperbed.
The reason you haven't heard of it, Mr. Scott, is because you haven't discovered it yet.
What? Are you from the future? Yeah, he is. I'm not. Well, that's brilliant. There's still enough sandwiches there. Well, she's a wicked dodgy. You'll do it as her. Totally by Jackson told a few other things. Let's go. So, the Enterprise has had its maiden voyage, has it? She is one well-endowed lady. I'd like to get my hands on her ample naysayers of your public engineering prowess. Except, from what I've done, which I don't, by the way. They're still talking about teaming up on the Enterprise while she's traveling faster than light without a proper escape pad. Get off there! It's not climbing straight. The notion of transwarp beaming is like trying to hit a bullet with a smaller bullet whilst wearing a blindfold, riding a horse. What's that?
Your equation for achieving transwarp beaming.
Imagine that. It never occurred to me to think of space as the thing that was moving.
And then Scotty has his realization where it's like, oh, space is the thing that's moving. I'm not actually traveling faster than light. I'm just getting to some place faster than light would be able to. And, you know, it kind of makes you think, like, at what point in the future do you think any of this will become realistic? So far, the fastest speeds we've ever achieved are on the order of tens of thousands of miles an hour, which is still much less than 1% of the speed of light.
Well, Cochrane has his warp drive, the same in 24 something, right? Or 23 something. So maybe 2410. So
Okay.
you have to do a lot in 300 years or 400.
We do.
Yeah.
Yeah. I think even just achieving 1% of the speed of light, getting any object to move that fast would be absolutely remarkable. I'm going to go back to earlier in the movie, so around 55 minutes. Or actually a little bit further, just about 1 hour. And we'll see an example of somebody getting beamed, somebody getting like disassociated, all the particles just vaporize and then reassemble in another location in time.
Retract the drill. Let's move out.
Yes, sir.
There you see they're about to smash into the ground. In the last second, the operator gets to split them all up into particles, and then they come back safely into the ship. And you often wonder if this really could happen to a human, what would be the resulting product that comes out on the other end? You know, are you still the same being? And this reminded me of a thought experiment called the Swamp Man paradox.
Ooh, where's that?
Yeah, this is a philosophical thought experiment that goes a little bit like this. So I'll read this little paragraph. Suppose lightning strikes a dead tree in a swamp. I'm standing nearby, and my body is reduced to its elements, all the atoms. While entirely by coincidence and out of different molecules, the tree is turned into my physical replica. My replica, who I'll call the Swamp Man, moves exactly as I did and encounters my friends and seems to recognize them and goes back to my house, and nobody can tell the difference. But is that ensemble of particles really the same person as me? And this is like a really tricky philosophical argument where it's like this new set of particles does not have any memories that the original one did. And so can it be argued that they are indeed the same person?
Well,
so
memories at some level are cellular particle, so why not?
It's interesting, yeah. Like, think about it. What physically is a memory? Like, think about your last birthday, for instance. Like, that memory of your birthday, you can think about where you were, who you were with, what the day was like. But where is it? Where is that memory? And
Stuart would have some thoughts about that.
Well, again, just to say what Deb just said, that it has to ultimately be coded in something in the brain that, is beyond our scientific ability now. I mean, there's all this issue about getting computers fast enough to be able to, form a neural net that has every neuron in the brain, but it's probably going to be many levels below that and much more complicated, maybe at the atomic level, to be able to reproduce everything. But, unless you believe in, you have a metaphysical view that there's something besides the brain and, besides science and 3 dimensions, then, eventually we have to be able to do it. And you're right. I mean, I guess there's some of these thought experiments about taking people's minds and preserving them in a computer and then putting them back sometime in the future. I mean, it's all kind of based on the same principle, but maybe maybe that's 1,000 years from now. I don't know.
yeah. Yeah, it's good that you mentioned computers, because I think there is a distinct difference between how computers store memory and how our brains store memory. Like, if you were to think of like, okay, where's my resume? It's a Word document, right? And the Word document has so many words, phrases, and letters arranged into a specific pattern. And that gets encoded onto a hard drive, where all of this data, zeros and ones, tell you exactly what that resume looks like, where all the letters are, and how many of them are there. But the brain, I think, is a little bit different. Just reading about the physiological brain, it's thought that memories are just little electrical impulses in between neurons across like these synapses. And you think about it, it's okay, if I try to recall like my birthday, I'm going to have so many connections through my neurons, so many electrical signals going off. And it's also a little bit volatile. Sometimes memories can be corrupted a little bit. Sometimes they can be lost entirely.
Or created.
Or even created out of nothing, like false memories. And if you would ask me what did I eat for breakfast 16 years ago, it's probably gone. It probably won't be retrieved again. And it's like, where did it go? So it's a really.
So you're right. So if it's not a computer, then that might not be enough for the right model. But, if you do a thought experiment, eventually we should be able to recreate, the atoms and the matter and how the and figure out how neurons work and, at least set up the starting point for somebody. We have no idea what it'd be like. That could be 1,000 years from now or 2,000 years ago. And whether you can recreate you right now or just the starting point, who knows? But, if you use the thought experiment and say, eventually we could deal with anything in the physical world, eventually, including the brain, I mean, you can at least feel like you can get into that territory someday. But
we really are electrochemical machines.
right.
And if you're replicating the mole on my arm, you're likewise replicating one neuron next to another. And what makes us forget, what makes a memory so remote that we can't remember, but sometimes you can stick an electrode into that particular neuron and you suddenly remember. As Stuart said, unless you believe in, have a mystical point of view, or you believe in the soul as opposed to us as mere mortals, it was a very delicately created electrochemical structure. If you can recreate the mole on my arm, you can recreate a memory.
I like to think of it that way, yeah.
Warp wise, transport wise.
Yeah, because you think about your brain is a physical object. It's a lump of fat and water, and it's firing off little electrical signals.
Yeah,
I like to think about this as what we're trying to do as human species now is reverse engineer 4 billion years of biology.
Yeah.
And we've been at it for a couple of hundred years.
Yeah.
So, we're just scratching the surface of being able to, figure out 4 billion years of evolution.
Mm-hmm. Totally. So there's another. Yeah, go ahead.
Well, I had another question about the movie. They seem, especially, I think the scene in particular is at the end, but they treat a black hole like a time warp. That they can go back and forth in time by going through a black hole.
Yes, I was just going to get to that. Perfect timing.
Okay, so go. Proceed, please.
Yeah. Just
now
where it was.
Looks like we can see something for the first
time. Yeah.
Okay, cool. Yeah, I remember watching the ship go through the hole, and it looks like it comes out the other end, back in time. 124, I think. This is where he's like,
yeah. Okay, you know that sign?
The Vulcan sign. Yeah.
The Vulcan sign. But do you know the thing about it?
No.
So Leonard Nimoy was an Orthodox Jew. And that is the sign of the priestly tribe bestowing blessings.
Interesting. I didn't know that.
Yeah. So the Levi priestly tribe, there are 12 tribes of Israel and all this. So the priestly tribe would do that with their hands, bestowing blessings.
I can't do it with my hands.
Well, you're not a Levi.
Yeah, I guess.
You're a Brodsky.
Okay, I think I found that scene where the ship is like going through the black hole and it acts as a time machine.
Here, that's it.
As I began my return trip, I was intercepted. He called himself Nero. In my attempt to escape, both of us were pulled into the black hole. Nero went through first. He was the first to arrive. Nero, his crew, spent the next 25 years awaiting my life. But what was years for Nero was only seconds for me. I went through the black hole. Nero was waiting for me.
It's a really confounding puzzle, even right now with the top astronomers. You know, what happens when you pass through the event horizon of a black hole? Now, the most information we have to date on black holes is those images we got 2 years ago of, you know, an actual event horizon, like the orange ring.
Yeah.
And that was from M87. So we don't know really what happens at the singularity. So the singularity is the center of the black hole, and it's where time and physics breaks down, and a huge question mark is put there. And it's been postulated by plenty of people that, you know what, maybe black holes could really be wormholes. They could transport us from one side of the universe to the other. And we don't have any evidence to refute that. We can't say for sure that doesn't happen. So, you know, the movie takes advantage of that. They exploit the black hole's properties and say, okay, nobody's telling us that it can't be a wormhole. Let's make it a wormhole. That's what ends up happening. And they do even get the time dilation effects correct. When you're in such a deep gravitational well, time dilation is really exaggerated. So when he said what was decades for one person could have only been a few seconds for somebody else. And that differential, right, when you're really, really close to a black hole's event horizon versus pretty far away, that discrepancy is enormous. Seconds can be stretched out to several years.
That's what they use in the movie we're going to see upcoming, Ad Astra.
Yeah, you're right.
Oh, I didn't finish that round at the first round. Okay. So what is the, to use the biological phrase, what is the life cycle of a black hole? To mix the metaphors here. How do they start? We know we have a vision, though now you're throwing in a wrench of their the middle, but what happens at the end of the life of a black hole? What happens when there's nothing else to eat? When the galaxy's all encompassed?
I think I learned this from a really exciting YouTube video. It's called like the timeline of the future, the very distant future of the cosmos. And so picture it like this: black holes exist right now, like we just took an image of one.
Right.
And we think that the ones we have images of have been around for at least a few billion years. But they really don't go away for a very, very, very long time. And we're talking like octillions of years into the future.
Yeah, but how would they go away? What would happen? You know, how would they dissipate or whatever, or implode or explode, or what do they do to go away, whenever that is?
Yeah. Stephen Hawking thinks they will evaporate. And they do this by sort of releasing these virtual particles. And now this
Virtual.
isn't
Yeah.
virtual particles. And this isn't a rigorous theory. This is very, very speculative. Because there's very little science and information about black holes.
Mm.
And
But
so
that's,
he's like, okay.
that
There
was
will-
where Hawking's got with the information. I think hopefully you're going to go there. Whether information
Yeah,
is
the information-
contained within the black hole or could it escape from it, I think is what you're talking about. He
Yeah.
changed his mind near the end of his life.
Yeah, exactly. Because when black holes take things in, they're taking in information. And Einstein says, look, or I don't know if it was really Einstein, but scientists say nothing can leave a black hole. Once it goes in, it's never coming out. And then we're left with like, okay, well, where does it go? And it's thought that like through Hawking radiation, are we breaking this law or are we diving into a new field of physics? And I'm going to just pull up some Wikipedia page because this is one of my favorite articles. It's a timeline into the future. Let's see what this brings up. Okay, timeline of the far future. And
Timeline
we
of
have
the
this
far future.
Really, yeah, we have this really beautiful catalog, and it says how many years from now, what will happen? And for instance, 50,000 years from now, Niagara Falls will erode away completely, and
Right.
we won't have any waterfall anymore. So that's just 50,000 years. And that's like tomorrow in cosmological terms. We'll go down to, let's see, 100 million years, and we think Saturn will lose its rings. And we'll go to 1 billion years. Earth's surface temperature will be around 115 degrees because the sun will be getting bigger and getting ready to eat the first 3 planets. Go down to 50 billion years. The Earth and the Moon are tidally locked to one another. That's if they haven't been already eaten by the sun yet. Now we're really diving into huge timescales. 1 trillion years from now, we think stars will no longer be. Stars will stop forming. And this is because dark energy is now dominating the universe, and there really won't be enough gravity to crush gas clouds into stars. So now we're going to find when do black holes evaporate? When is the last black hole going to be around? So let's look. I think first, smaller black holes will be eaten by bigger black holes. So supermassive black holes, like the ones you would find in the center of galaxies, are going to start eating smaller black holes. And then those will be the only things left in the universe. When those black holes evaporate,
Iron stars collapse and assuming no proton decay.
okay, so black holes will be the only thing left in the universe in about 10 to the 43 years. So that is like 1 vigintillion years. And we'll only have black holes. And then it will take many more orders of magnitude for them to disappear. So we're talking like 10 to the 50 years, which is a number I can't even write.
Well, So black holes don't go away. They're
Okay,
just
here. They're very hard to go away. They don't go away very easily. So the largest black hole we know of, called Ton 618,
yeah.
may dissipate by the emission of Hawking radiation in about 10 to the 99 years.
So this timeline
Which is just a
doesn't
Mhm.
this doesn't have multiple universes. It looks like at the end it's just, what is it? The death of our universe. What's the very end of this timeline?
Yeah, the very end of this timeline is time for quantum effects to generate a new Big Bang, resulting in a new universe.
Okay,
And that will occur in 10 to the 10 to the 10 to the 56 years, which is a number so absurdly big that there isn't
not gonna
enough
wait around
room for me to write a number. And I won't be able to. I will have quantum tunneled into some black hole by then, if I'm immortal.
Yeah.
Well, what was the other phrase that it came up? Sam mentioned it. Instead of Big Bang, it's not the big pulse, but
The big rip or the big crunch.
no.
Yeah.
Not the big rip or cry. It's more like to indicate that there's a vacillation. It comes and
Oh, the big bounce?
the big bounce. Yeah.
Okay.
Yeah.
That's probably what this last bit of notes is about. Yeah, for a new Big Bang to happen.
Well, isn't there a number of theories that in cosmology that say that could potentially be a much closer tie-in with black holes and new universes, in the sense that both of them are singularities, so the physics of what happened at the beginning of our Big Bang is a singularity going the other direction from the singularity at the very center of a black hole. So I thought there was a lot of people, and I thought including Hawking at the end, that he was speculating these are tied together that way somehow. At least
That's
what
a
you
really
think about that.
That's a really good thought. Yeah, the Big Bang is sort of the opposite of a black hole.
Yeah.
It's like the yin and yang.
Mhm.
But the black hole has a singularity that everything goes into, and a Big Bang is a singularity that everything comes out of.
Yeah, and I thought he was talking about that near the end, and maybe other physicists are too. But I'm not I don't never follow that up then.
Mhm.
But I've heard that being talked about in the last few years.
Yeah, I do like that a lot. I appreciate that. Let me see. Oh, there was one little bit about the video where he talks about red matter.
Yes.
And it's like-
What's with the red matter?
That was that was a surprise to me. I was like, oh look, they came up with some exotic matter. And
None of this stuff that you're showing can really be heard. So I think if you're going to do this and put it out as a YouTube, it's probably worth redoing it maybe once you get the video working.
okay, yeah, I may have to just look at the audio once it publishes. Maybe the recording will have picked it up. I'm not sure.
Yeah, maybe.
We'll see.
Yeah.
Okay.
But and it's hard for us. We can hear, but we can't hear well.
And can't see anything either.
Okay. Yeah, we can see this, but you can't see it when you're playing it somehow.
I don't know what it is. I'll have that fixed for next time, because what I am using is a new microphone, and I have a brand new laptop that I recently got.
So while you're looking, are you called Wyoming Stargazing in Tucson?
We're Wyoming Stargazing. We're doing business as Stargazing USA. Since
Like if I were to have my friends look you up, who do they look for? Stargazing USA?
If you want to go to the website, it's the same website, just wyomingstargazing.org, and you can find 2 science programs on that whole
Okay.
page.
Star and supernova. I analyzed the wonders of our sacred planet. We outfitted our fastest ship.
So I have it here. I have the ship.
I would create a black hole, which would
So he says he has this orb of red matter, and he can use it to create a black hole. What I'm going to do is just take a screenshot and put it on a brand new document. So you can just at least have a visual of what it was. That's weird. Let me take a screenshot. I wonder if
could absorb the exploding star.
You're seeing what we're seeing now.
yeah, that's weird. Oh, it's like preventing me from sharing the video. I wonder if it's has to do with a copyright thing. That like
Oh, yeah, yeah, could be copyright, yeah.
I have to ask Sam how he did this then. Because if he was using Amazon Video, how is he able to share the screen? Okay, all right. Well, I'm glad I saw that.
Mm.
It wasn't just us in our minds, just imagine.
Okay, that's good. Yeah. Well, here's a Wikipedia page that talks about exotic matter, and it's completely hypothetical, so maybe you can get away with it. It's not false by any means. And let's think about it. We don't even know what dark matter is, and we know it exists, but we're in the dark about it. And so, yeah, you can call it red matter, purple matter, polka dot matter, what you want, and give it any property you wish. Because, look, there's stuff that really exists in our universe, and we don't know what it's all about. Antimatter, negative energy, negative mass, strange matter, mirror matter.
But this red matter in the film, in the poetic license of the film writers, created black holes, right?
It did, yeah.
And not much. So they injected it into Vulcan. Vulcan turned into a black hole.
Yeah, so he took a little capsule of red matter and threw it into a star that was about to go supernova and turned it into a black hole.
Ah, yes, that's at the end, yes.
And what's interesting is, now I'm just thinking about this now, I don't think you really require any strange matter to make something into a black hole. If you just pack enough matter into a small enough space, you'll eventually get a black hole. For example, if you pack the mass of the Earth into this Wikipedia logo, you'll probably get a black hole.
Mm.
And some stars, when they die after neutron stars become black holes, or could.
Yeah. Yeah, and the type 1A supernova is like a vampire star where it's sucking matter from its companion and accruing so much mass that it reaches a limit, they can't take our limit, and then bang. It can't take it anymore, and then electron degeneracy pressure blows the whole thing apart in a supernova.
I gotta go. So my only last comment was, we human beings like know answers to things. So the idea that we don't know answers to a lot of this stuff is uncomfortable. But, you know, we don't know answers to a lot of the universe. So,
Right.
yeah.
It's an interesting point of view. I don't think Richard Feynman had that point of view. Richard Feynman is quoted saying, "I'm not scared of not knowing."
Yeah.
He thinks it brings him excitement.
Yeah. Mhm.
Take care. Let me go.
Okay. Bye, Stuart.
All right, see you later.
Wait,
Um,
I'll put myself back on. Hi.
okay. I think that was all I had prepared for Star Trek.
Okay.
To talk about the black hole, the time dilation, lightning, and
So here,
time-
create a watch party. Whatever that is. Yeah.
Oh, maybe I'll try that feature next time. It'll work a little better.
What was
Yeah,
that?
I have to ask Stan about what that issue was, why the video wasn't showing.
Yeah.
But that's all right. Did you have any questions for me at all?
I think we covered the questions that I had as I watched the movie. Yeah.
All right.
Because yeah. So, yeah, aside from the technical issues, it was good. So thanks.
Great.
Yeah.
I'm glad you enjoyed it.
Yeah. Yeah. So is it next week? We're doing it every week?
Yeah, I'm gonna be doing it every Wednesday.
Okay.
I have
All right.
I have the time now to be able to do it every week.
So next Wednesday, I'll get my second COVID shot and I'll see you later.
Okay, sounds good.
I'm of the old enough group. And so is Stuart. I don't know what his deal is though. Okay, well, thank you. Okay,
No
do you have
problem.
anything else or words of
No.
advice or?
Stay safe out there.
Yep,
and
you
stay
too.
curious.
Yep. Arizona is a dangerous place.
Yes, I'm quite aware, but we're doing well.
Okay, good. Okay, take care. See you next week.
All right. You too. See you then.
Bye-bye.